So transistor biasing. So we know what is biasing. We had studied in diodes. So the supply of suitable external DC voltage is called as biasing. Now either forward or reverse biasing is done to the emitter and collector junctions of the transistor. So we took an example of NPN transistor. We saw how it was forward biased, and one part was forward biased, the other part was reverse biased. That is, in NPN we studied that the emitter base junction was forward biased and the collector base junction was reverse biased. Now one question arises: is always emitter base junction should be forward biased and collector base junction reverse biased, or can we do any other biasing also? Yes, if we do other biasings, what will happen? That will be the next question. So now we see that these biasing methods make the transistor circuit to work in three kinds of regions. That means if the emitter base junction is forward or reverse biased, collector base junction is forward or reverse biased, what happens? So we can have three different combinations, and for three different combinations we will be having the transistor working in three different regions. So the three different regions are active region, saturation region, and cutoff region. So please concentrate on this very much, and your further topics rely on these only. So now the VI characteristics of a transistor. So here you can see the collector current IC on the y-axis with VCE, the voltage across, the output voltage, the voltage across the collector and the emitter. When we take this, we see the characteristics are obtained in this way. So you can see the graph with blue lines here. So the graph will be obtained in this way. And this is the DC load line, the red mark. Now here you can see here the lower portion. Here you can see this lines here. This lower portion is called as cutoff region of the transistor. So in the cutoff region, the transistor is fully in off condition. That means it is off. Transistor is switched. Now you can see a curve going like this, and before that part you can see one more lines shaded here, and this part is called the saturation region where the transistor is on. And this remaining part which is not shaded but has this curves here, okay, so this full part is called as the active region. So remember, the transistor based on biasing conditions will be having different regions, and it will have three different regions, namely the active region, the saturation region, and the cutoff region. Now our question is, when do we say the transistor is in active region? When is the transistor said to be in saturation region? When the transistor is said to be in cutoff region? So down here you can see a table here. This is very important. Emitter junction and collector junction. We have to consider these two junctions because the transistor is having two junctions, we know, between emitter and base one junction and the other junction at the collector and base terminal. Now, when a emitter junction in a transistor is forward biased, it can be either in PNP or NPN configuration. And at the same time, when emitter base junction is forward biased and the collector base junction is reverse biased, then we say the transistor is being operated in active region. That means this region. Okay. Now, similarly, if the emitter base junction is forward biased and even if the collector base junction is also forward biased, then the transistor will be operating in which region? Saturation region. That means here, this part. Suppose the emitter base junction also is reverse biased, and if we reverse bias even the collector base junction, then what happens? The transistor off. So that time we say the transistor is being operated in cutoff region. So this is the important table what you people should know, and based on this only we will be moving forward. So remember, when the EB means emitter base junction is forward biased and CB is reverse biased active. When both are forward biased saturation, when both are reverse biased, transistor is said to be cutoff region. So this you people should know. Active region. Now we know this is the region in which transistors have many applications, and this region is also called as linear region. And when the transistor is in active region, we can operate this, or this can be used as an amplifier. So we saw operational amplifiers, then we were using op-amps, but we can also make use of the transistor work as an amplifier. So how do we make that? By making the transistor to operate in active region. So how do we make the transistor to operate in active region? By making one junction forward biased and the other junction reverse biased. Now the following circuit diagram shows a transistor working in active region. So this region lies between saturation and cutoff. Which region? Active region. Okay, as we saw in the graph. So the transistor operates in active region when the emitter junction is forward biased and collector junction is reverse biased. So instead of every time telling emitter base junction, as soon as we say emitter junction, it is understood that it is the junction between emitter and base. And similarly, when I say junction, it is clearly understood that the junction is between base and the collector. Now in the active state, collector current is beta times the base current. That is, the collector current is denoted IC. You can see in this figure IC here, collector current, and this is beta times IB we saw in the previous equations. And IC is the collector current, beta is the amplification factor, that is current amplification factor, and IB is called the base current. So here you can see here that IB current is flowing and B is forward biased and IC is beta times IB and C is reverse biased. Now next region is saturation region. So we know from the table that the transistor operates in saturation region when both the junctions are forward biased. Now when the transistor is in saturation region, how do we make use of the transistor? The transistor tends to behave as a switch, the two in closed form. That means the transistor can be made to be used as a closed switch when we operate the transistor in saturation region. In other words, we can say the transistor can be used as a switch. We forward bias both the junctions. That is the meaning. Now the transistor has the effect of its collector and being shorted, and the currents, both the currents, collector and emitter currents, are maximum in this type of operation. So now you can see here So in saturation region, shortly we can show that collector and emitter is shorted directly. That means almost all the current of emitter is equal to the collector of the, equal to the collector current. But in the circuit, we have to show in this direction. So the arrow mark is being shown like this. See here, now no connection here. Now, so in saturation mode, these are the equations. Beta will be less than IC by IB. And as in the saturation region, the transistor tends to behave as a closed switch. Almost the collector current will be equal to the emitter current only. Now the last region is the cutoff region. So we know that the transistor operates in cutoff region when both the junctions are reverse biased. Now, when we reverse bias both the junctions, in what way can we make use of the transistor? The transistor tends to behave as open switch. So see here in the circuit diagram, there is no connection at all. So no currents are flowing, hence the transistor is off. So we say it is an open switch. And the transistor has the effect of its collector and base being opened. And the collector, emitter and base currents all are zero in this mode of operation. And same thing is written here in this equation. So in cutoff region, the collector current, emitter current and base currents are nil. So we are writing this. IC equals IE equals IB, all are 0. Now, you people will be telling me one by one. BJT as an amplifier. BJT is nothing but again a transistor. So from here, your module 4 topic starts. BJT as an amplifier. So before knowing this topic, the previous slides, whatever we had discussed, that is the basic fundamentals you should know to read this topic. Okay. So now you tell me, transistor is nothing but your BJT only, bijunction polar transistor. Now as an amplifier, so just now we saw, when do we say that transistor can be operated as an amplifier? So when one junction is forward biased, the other junction is reverse biased. So as you have learned, a transistor amplifies current because the collector current is equal to the base current multiplied by the current gain. And the base current in a transistor will be very small compared to the collector and emitter currents. And because of this, the collector current will be approximately equal to the emitter current. So now based on this, we will look at the following circuit. See here, this is the circuit for transistor working as an amplifier. See here, the transistor here, this is the base, this is the emitter and this is the collector. Emitter is grounded directly. You can also make use of one resistor here. And to the base, you have one resistor RB connected. And the base voltage VB is measured from the terminal from the base terminal to the ground, and that voltage is VB. Now you can see the source voltage here. This is AC voltage. It is denoted as VS, source supply voltage. And here through one capacitor. Capacitor is optional here. So we know that it blocks DC and allows AC components. And here again, you can notice in the circuit, one more DC source is added here. We call it as VBB because it is connected at the base. This is AC source and one DC source. Both are connected together. Now, when both are connected together, how do the input signal look like? So from this graph, you can see here, the signal has been raised a little here. Usually at 0 itself, we used to draw the signal like this. But here you can see at VBB, VBB is acting as the DC supply voltage. Upon that, the AC signal is superimposed. So this signal, the curve, sinusoidal signal is your VS signal coming from AC source. And this VBB, that straight line you can see, that voltage is coming from this DC source. Suppose if VBB is 5 volts, then in the graph you see this is 0 volts. Here at 5 volts, you can draw the sinusoidal signal. So it will be raised. The signal will be raised and it will be superimposed at 5 volts on the DC signal. This is how it is connected. And now here you can see the another supply voltage at the collector part and one resistor connected across the capacitor. So you can consider the RC itself as the load I told you in the previous slides itself, RC or RL. So here it is shown as RC, that is the resistor connected across the collector. And this is RE dash is the internal resistance. Now, after this is the input signal. After operation of this, the output signal is shown here. Now see, the signal is amplified but inverted. Why is the signal here inverted like this? Because one is here, it is forward biased. Here you can see it is reverse biased. So here, as soon as the supply is on, this DC signal and the AC signal is superimposed on the DC signal, the current IB flows through the transistor circuit towards the base, and the small current, the IB, which is very small, this current results in a very large flow of collector current at the circuit, which gives us an amplification of the signal. So we call this transistor as a current controlled device. That is, at the input we have a small current controlling the large collector current at the output. So we call this as current controlled device. So this is the transistor operation as an amplifier. The same thing I had explained here. So we saw the circuit here. So an AC voltage is superimposed on the DC bias voltage, and capacitive coupling is shown. The DC bias voltage is connected to the collector through the resistor RC. Same thing has been explained here. And the AC input voltage produces base current, which results in larger AC collector current, and this collector current produces a voltage across RC, thus producing an amplified but inverted reproduction of the input voltage in the active the operation. And the forward biased base emitter junction presents a very low resistance to the AC signal, and this internal AC emitter resistance is designated in the figure, that is, I have shown that, and it appears in series with RB. That is, that small RE dash you can see there in the circuit, that appears in series. Here, this appears in series with R. Now we have few equations to note down for that purpose. Now the AC base voltage is given as VB. So we saw that blue voltage there connected from, measured from the base to the ground, and that VB is given by, we know, by ohm, is the product of the resistance and the current. So here we have taken IE into RE dash. The AC collector voltage VC is given by CRC, and since IC is approximately equal to the collector voltage, emitter current, the AC collector voltage is given by this equation VC, which is approximately equal to IE into RC. And VB can be considered the transistor AC input voltage, where VB is equal to Vs minus IB times RB. So how did we get that equation? So see here in the circuit, here, this part. So here you can guess Vs minus VB times IBRB is that equation. This part. VB is Vs minus IBRB. That means we are applying KVL at the input circuit. And VC can be considered the transistor AC output voltage. And since the voltage gain is defined as the ratio of the output voltage to the input voltage, now take the ratio of both, that is VC to VB, which gives the AC voltage gain. And the AC voltage gain is denoted as capital A suffix V of the transistor. And this AV is equal to VC by VB. So since RC is always considerably larger in value than the output voltage, now for this configuration is greater than the input voltage. Now you substitute this IERC for VC and IERE dash for VB, then you will finally end up with this equation. AV is equal to VC by VB, which is approximately equal to IE into RC by IE into RE dash. Now both the terms will get cancelled, IE. So you will be left over only with RC by RE dash. So this gain can be calculated only if you know these two resistances also. That is the meaning. Now here is one problem. You can go through this problem. Determine the voltage gain and the AC output voltage in this figure. So you put that RC by RE dash, directly the values are given, and you will be ending up with gain, and you can calculate directly the output voltage AV times VB. You're given with all the values, you can calculate that, and this will be in terms of RMS value. Now BJT as a switch. So again we saw that when the transistor operated in saturation region, it will act as a closed switch. When it is operated in cutoff region, it will act as an open switch. By making use of those two combination, we can operate transistor as a complete switch. So here we will see one figure that forms the basic operation of BJT as a switching device. So we know the transistor is in cutoff region because base emitter junction is not forward biased, and there is an open between collector and emitter, and that is shown in one figure. And in the other figure, the transistor is in saturation region because the base emitter junction and base collector junction are forward biased. So in this condition, there will be a short and a small voltage drop across the transistor. Now see here, you have two circuits here. This is first diagram shows that the transistor is acting as an open switch. You can see here the symbol RC, and here the current IB is 0, IC is 0. So now this connection, collector and emitter connection, can be shown as a switch. In cutoff region, it will be open like this. And here you can see the saturation, in the saturation region, it is acting as closed switch. Okay. That means there is a connection between emitter and the collector. So in saturation, both are forward biased, and here both are reverse biased. So same thing, you have few equations here. Conditions in cutoff. So we know what is cutoff region. So that is when the transistor is in cutoff, we see that VCE will be equal to full VCC, and in saturation, the current IC in saturation will be given by VCC minus VCE by RC, and the minimum value of base current will be IB is equal to IC time by beta times DC. This equation we know from the beginning. So normally IB should be significantly greater than IB minimum to ensure that the transistor is saturated. So for this ensuring the transistor, here you have a problem. So you can look into this problem and solve this problem. So I'll put the problem in the Google Classroom. You can try out. Later we will discuss.
Roshan.